we want to determine algebraically. So that means we're going to do the algebraic work of, in the equation, switching the x and the y and solving for y, and find out if they're inverses of each other. Then we're going to look graphically if we could tell the same thing. So algebraically says take one of them. I'm going to take equation 1, switch x and y. And then solve for y and see if it matches up with equation 2. So to get y by itself, I could add 6 to both sides and divide by 3. And I get y plus 6 divided by 3. Does that match equation 2? No. So algebraically, we can see that they're not inverses. Okay? Graphically, I'm going to change this number 2 to green. Graphically, for that same question, our blue equation was y equals 3x minus 6. And our green equation, well, I'll graph the blue one first. 1, 2, 3, 4, 5, 6. So we would have y-intercept of minus 6, a slope of 3, so we go up 3 over 1, up 3 over 1. There's our blue graph. Our green equation okay. First of all, before I go too quickly into the green equation, if you look at the green equation, do you know what kind of graph it is? And if you know what kind of graph it is, and you know how to graph that kind of graph, why does this one seem hard to graph? Okay, so first of all, do you recognize that's a line? Just like the blue one is a line. The blue one was nice because it was in y equals mx plus b form already. The green one needs some rearranging. So a lot of the things that you see happening from, I think probably starting this year and even more next year, is we have to be strong in our algebra skills so that when we see something, we can play around with it, rearrange it. Can you see that you could write both of those things divided by 3? And then if both of them are divided by 3, well, x divided by 3, you could write as 1/3 x. And 6 divided by 3 as minus 2. And now it's like, oh, so my y-intercept is at minus 2, and I have a slope of 1/3, meaning I go up 1 over 3, up 1 over 3. And I draw this. So how can we tell from the graphs that they're not inverses of each other? Well, a couple of ways. If they're inverses of each other, they would flip over that line. And if things flip over that line, well, this blue point should have been on both, and it's not. This green point then should have been on both, and it's not. Some other ways that we can see that graphically this doesn't work. On the blue graph, can you see that you have the point 0, negative 6? But at negative 6, 0, there's no graph. And graphically, if you would switch the x and the y points on an inverse, that would show up. So let's look at the second one. The second one, we've got a parabola and a square root graph, but with the parabola, we have a domain restriction. So this part here is telling us that we only have half of the parabola, only when x is bigger than or equal to 0. So if we wanted to do this algebraically, when you switch x and y, I would get x equals negative y squared plus 3. And now when I switch them, because I used to have x is bigger than or equal to 0, now I only consider this when y is bigger than or equal to 0. Because not only do the x and the y switch in the equation, they switch everywhere. Okay? And so if I was solving this, well, I could subtract 3 on both sides. If I wanted to get the y squared by itself, could multiply by a negative, and when I square root, you get plus or minus but since y has to be bigger than or equal to 0, it's only going to be positive 1 or the negative 1? The positive 1. So that y being greater than 0 tells us we're only going to get half of the inverse too, because if you have half the parabola, part of it's going to be gone. You're not going to have the full inverse either. You're only going to have one of those two square root functions. And in this case, since the y was greater than 0, you would have to have the positive 1. Okay? Does this match up with the equation? They have 3 minus x. We have negative x plus 3. Is it the same as that? Yes. Again, a little algebraic manipulation. Adding and subtracting doesn't matter the order, but it might be just enough to throw you off, right? So we got to be careful to recognize that negative x plus 3 is the same as 3 minus x. So that was algebraically. Graphically, again, I'm going to number these, the first one in blue, the second one in green. Negative x squared plus 3. So the negative would flip it down. The plus 3 would move it 3 units up. Over 1, down 1, over 1, down 3. And we only have this half because the domain restriction was x is bigger than or equal to 0. Those are some points on that graph. Now, graphing y equals 3 minus x, or y equals negative x plus 3. First of all, using our transformations, can you see that this one is the easier one to use? Because we usually have x first and then translations afterwards. Okay? Can you see that everything's horizontal in here? Horizontal reflection with the negative, horizontal translation with the 3. How many people in their mind are going, I remember to write it in factored form at this point? Or did it catch you again? Can you see whenever you have two horizontal things, you would need to rewrite this by factoring out that negative. so that your negative would flip your square root graph horizontally over the y-axis, and then we're going to move 3 to the right. Moving 3 to the right, that will get us to 3, 0. We would have 2, 1, and we would have negative 1, 2. Look at that reflection over the line y equals x this time. They cross at the right spot. Looking at the points are switches of each other. So both graphically and algebraically, these ones are inverses of each other. Okay, so for practice, you're going to try from the homework 7, 8, 11, and 13. And in my notes, I put a little star beside 11 and 13, that the way they've worded those questions, they're a little bit different. So we want to start having practice with a few questions that are a little bit different so that we can increase our problem-solving skills. And when you get to the exam and they put 1 or 2 on your exam that they try to word a little bit different, you're prepared for that.